Good morning, dear students. Today we discuss about general terms related to electrolytic conductance. Okay, so you have heard these words in your previous classes also and your physics classes also. So these are not new terms for you. Okay, so the first term resistance, which is represented by R, and the unit of resistance is ohm. Then the second term is conductance, which is represented by C, and it is reciprocal of resistance, which means 1 by R. And the unit of conductance is ohm inverse or mho, or we can say that Siemens. The third term is specific resistance or resistivity, which is represented by rho. We know that R is equal to rho into L upon A. It means resistance is equal to resistivity into length upon area. So we can say that rho, or the resistivity or specific resistance, is equal to resistance into area upon length. So in case of electrolytic cell, here L is the distance between the two electrodes and the A is the area of the electrode. So rho is equal to RA upon L, where R is resistance, L is distance between the electrodes, and A is the area of the electrode. The unit of specific resistance or resistivity is ohm meter or ohm centimeter. There is one thing to remember, that A or L for a given cell will be constant. It means area of the cell or the distance between the electrode for a given cell will be constant. So it is known as cell constant. Okay, when area and the distance between the electrode for a given cell will be constant, then it is known as cell constant. So cell constant is equal to distance between the electrodes upon area of the electrode, and the unit of the cell constant is centimeter inverse. So if we have a cell, and in this cell, if L is equal to 1 centimeter, or the distance between the electrode is 1 centimeter and the area of the electrodes is 1 centimeter square, then we can say that rho is equal to R, which means resistivity or specific resistance is equal to resistance. So from here we can say that resistivity of an electrolyte is the resistance offered to all the ions of that electrolyte present in 1 ml or 1 centimeter cube solution. Okay, resistivity of an electrolyte is resistance offered to all the ions of that electrolyte present in 1 ml or 1 centimeter cube solution. So the fourth term is conductivity or specific conductance, which is represented by kappa, or we can say that K. So kappa is equal to 1 upon rho, or 1 upon resistivity or specific resistance. It is reciprocal of specific resistance. So the fourth term is conductivity or specific conductance, which is represented by kappa or K. It is reciprocal of resistivity, or we can say that it is reciprocal of specific resistance. So here K is equal to 1 by rho. K is equal to 1 by rho, and we know that rho is equal to Ra upon L, where R is resistance, A is area of the electrode, and upon L is distance between the electrode. So we find 1 upon R into L upon A. We know that 1 upon R, or the reciprocal of the resistance, which means conductance, and L upon A is cell constant. So we can write that conductivity K or kappa is equal to conductance into cell constant. Conductivity K or kappa is equal to conductance into cell constant. And the unit of conductivity is mho inverse, ohm inverse, or centimeter inverse, or we can say that mho centimeter inverse or Siemens centimeter inverse. Conductivity is conductance due to all the ions present in 1 centimeter cube or 1 ml of electrolytic solution. Conductivity is conductance due to all the ions present in 1 centimeter cube or 1 ml of electrolytic solution. Okay, then come to next point, molar conductivity, which is represented by lambda m. Molar conductivity lambda m. This is new term for you. So the molar conductivity is the conductance due to all the ions of that volume of electrolyte which contains 1 mole of electrolyte. Okay, conductance due to all the ions of that volume of electrolyte which contains 1 mole of electrolyte. So lambda m is equal to kappa or conductivity into volume V, and this is that volume which contains 1 mole of electrolyte. So molar conductivity is equal to kappa into V, and if we have molarity, then to find out V, we can write it like m is equal to, or molarity is equal to, moles of solute upon volume solvent in liter. Okay, then we can say that molarity is equal to 1 upon V in liters. V in liters is equal to 1 upon m. We can write that. Okay, and to convert it in centimeter cube, V centimeter cube is equal to V in liters into 1000. We have to multiply 1000 to convert it into the liters, okay, or centimeter cube. So from here V is equal to, or volume is equal to 1 into 1000 upon molarity. Okay, so we have to put this value into the equation, that is lambda m equal to K into 1000 upon molarity. Okay, so unit of molar conductivity is Siemens centimeter square mole inverse. Siemens centimeter square or mole inverse. Then come to equivalent conductivity. This is same as the molar conductivity, but here we have to write equivalent conductivity, which is equal to K kappa into 1000 upon N, and here N is normality, not molality. It is normality, and the unit of equivalent conductivity is Siemens centimeter square equivalent inverse. We can say that equivalent conductivity is the conductance due to all the ions which is present in that volume of solution which contains 1 gram equivalent of electrolyte. Okay, equivalent conductance is the equivalent conductivity is the conductance due to all the ions which is present in that volume of solution which contains 1 gram equivalent of electrolyte. So here we discussed some terms related to our new topics. So before that we have to calculate some numericals. Okay, so the first is for 0.01 N NaCl solution R equal to 200 ohm at 25 degree Celsius. If cell constant is unity, then calculate equivalent conductivity. We have to calculate equivalent conductivity. So we have resistance and normality 0.01. So equivalence conductance is equal to kappa or conductivity into 1000 upon N. So is equal to conductance into cell constant. Okay, and the conductance is the reciprocal of resistance. So we can write that 1 upon R into cell constant is 1. Cell constant is 1. So it is 1 upon 200 K kappa. Conductivity is 1 upon 200. So equivalent conductivity is 1 upon 200 into 1000 upon N, that is 0.01, and it is equal to 500 Siemens centimeter square equivalent inverse. Then come to second numerical, in which is for a DC normal solution, resistance of an electrolyte is 3.2 ohm. If distance between electrodes is 1.8 cm and area of electrodes is 5.4 cm square, then we have to calculate cell constant, specific conductance and equivalent conductivity. Here we have resistance 3.2 ohm, length or the distance between the electrodes is 1.8 cm and the area of the electrodes is 5.4 cm square. So to calculate cell constant, we have the formula distance upon area, which is 1.8 cm upon 5.4 cm square, and it is 1 by 3 cm inverse, which is equal to 0.33 centimeter inverse. Okay, then we come to specific conductance, and we know that specific conductance is equal to conductance into cell constant. Okay, and we know that conductance is reciprocal of resistance, so we can write C as a 1 upon R or 1 upon resistance into cell constant. Here cell constant is 1 by 3, then we get the value 1 by 3.2 into 1 by 3, that is 1 upon 9.6 Siemens centimeter inverse. Then we have to calculate equivalent conductivity, and we know that for equivalent conductivity the formula is kappa or the conductivity into 1000 upon N. Here kappa is the conductivity and N is normality. So from this 1 upon 9.6 into 1000 upon 1 upon 10, because we have a DC normal solution, so we can write 1 upon 10. So from it we get 1 upon 9.6 into 1000 upon 0.1. So it is approximately 1041.66 Siemens centimeter square equivalent inverse. Okay.